Okay, so this is one of my favorite lectures in the entire course. Let me turn the volume down here a little bit. I hope it becomes one of your favorites too, okay? It is just too beautiful how the mathematics works out on this problem. So, now, maybe I've set the expectations and the bar way too high and I'll underperform, but I call it what we're going to arrive at as the unexpected inner product, okay? So we'll see if you get a sense of my wicked humor on that. So, a little bit of background. We've been doing fitting problems, trying to estimate parameters on the basis of measurements. So we did deterministic weighted least squares. And once again, there is no probabilities anywhere in the problem statement. So we have an unknown x, it's a constant, we have measurements of it, y. The equation y equals cx is not consistent. Y does not equal cx for any x. And so we called those overdetermined and we were finding solutions that minimize the error when you did y minus cx. We're really minimizing this parameter here, e, which is what you have to add to the equations in order to explain the mismatch in y minus cx, okay? So it explains the mismatch in what you're measuring, how these equations supposedly arrived, and the measurement. And so we set up a least squares problem. We did it first with the weight term being the identity matrix, and then more later we put in an arbitrary positive definite matrix in here. And the solution, when you do that, is C transpose S, C inverse, C transpose S, Y. So it's a linear function of the measurements to recover your best estimate for X. So that's deterministic weighted least squares. And then a week ago today, we did blue, best linear unbiased estimator. And this is the first time we threw in a model of how these measurement errors occur. So what we did was assumed these things have zero mean. If they have a constant mean, we can just subtract that off of y and get a new y that has, so it has zero mean. So that's not a big deal. And then we introduced something called the covariance, which looks at how various components of this measurement area are related one to the other. And then on the diagonal of this matrix, you have the variance of epsilon 1, epsilon 2, epsilon m. Okay, so we assumed that covariance matrix was positive definite. And then we had the rank of C is equal to the n, which is the number of columns, so it has full column rank, just as we did in weighted least squares. Then the problem was if we just tried to find a linear solution, in general, it would not have the property that the mean of our estimate would be equal to x. So we had to introduce this term unbiased. And so unbiased meant that however we form this estimate, its mean value should be the unknown x. So you want it to be spread around the mean and not shifted and spread about some other point that's disjoint and distinct from x. So we had this kind of strange constraint that we had to do, which is if we do a linear estimate, so gain times y, just like we have in weighted least squares, we had to impose that k times c is I. So that was came from the unbiased quantity. So best linear unbiased, so linear and unbiased, and best we decided to use the minimum of the variance. We tried to minimize the variance in our estimate. Okay, so we minimized the variance. So we had, our gain was an argmin of the variance of x subject to Kc equals I n by n. And this is really a quadratic program. So if you attended Bobby's lecture this morning, you saw him using quadratic programs. And as I mentioned on Tuesday, you would have these inequality constraints in general instead of linear. And then we had a solution to the best linear unbiased estimation problem. And this was kind of satisfying because we see it looks exactly like weighted least squares, where the weight is the information matrix of the noise. So that's the blue. Weighted least squares in blue are identical when you have the weight matrix chosen as the information matrix. Okay, so today we're going to do general minimum variance estimator. So I'm just reminding you that if we have a random vector with n components and it has a mean, that if we write down the variance of x, x minus the mean times x minus the mean, I guess that should be transpose here. This is the covariance I've written down. So we'll correct that. Okay, so that's the variance now. Row vector times a column vector. The variance is a scalar. So it's the sum of the squares of the components, x transpose x. And expectation is an integral, and the integral of a sum is the same as the sum of the integrals. And so you get that the variance of x is the variance of each of the components of the vector. Okay, so the variance of a vector is the sum of the variance of each component of the vector. Okay, variance of a vector is the sum of the variances of the individual components. And so we're going to take advantage of that observation, because if we're trying to find an estimate that minimizes the variance, we can minimize the variance of each component of the estimate, and then we will have minimized the variance of the sum. Okay, so that's the review. Questions on the review? Cool. Okay, so let's start with our minimum variance estimator. Supposed to be blue. Minimum variance estimator. So it's typically abbreviated MVE. Okay, so we have RLS for recursive least squares. We have blue, best linear unbiased estimator, MVE, minimum variance estimator. These are all the types of different problems that we've been looking at. Okay, so here's the model. Y equals CX plus epsilon. So it's the same form we've been looking at. Y is in Rm. X, the unknown, is in Rn. And epsilon, the noise, in Rm as well. Here are the stochastic assumptions. Okay, so for the means, we're going to have expected value of x 0 and the expected value of the noise term, which is 0. So already you see this is different. We're now giving ourselves some side information about x. It has a mean value, and if you don't like the mean value being 0, just define a new x being x tilde x minus the mean, and you reduce it to this problem, okay? So this just makes the things easier, but now we no longer have only stochastic assumptions on the noise, but the thing we're trying to estimate has some random properties as well. And then we're going to have covariances. So the spread about the means and so just as before, the covariance of the noise will be Q. This time we're introducing covariance of the unknown variable x. That'll be called P. And this is a simplifying assumption that can be removed if we want. The unknown x and the perturbation on the measurements are uncorrelated. Okay? So your measuring device is not affected by the uncertainty in the thing that you're measuring. It's got its inherent way of generating perturbations in it. Okay? So it's uncorrelated between the measurement noise and the state. Okay? One says that epsilon and x are uncorrelated. Okay, assumptions. Q is positive semi-definite. P is positive semi-definite. And then there's one more that looks really odd at first, the first time you ever see this problem. C times PC transpose is positive definite. Okay? Excuse me?
Matrix inversion?
Maybe. That's a good guess. So later we will relate this to linear independence of some vectors. Okay, so this is the problem statement. We now have side information about how x is distributed. So it's the same linear problem we've studied many times. We first started out with no stochastic assumptions whatsoever, and then we had only stochastic assumptions on measurement error. Now we have some a priori information about how x is spread about its mean. And so once again, I don't really care that x has 0 mean. It's up in this quadrant. I just move my coordinates to here, and it's now 0 mean. But I know how it's spread. So that's just have high variance, low variance. And then what I want to do is take the measurements and reduce the uncertainty in x. That's my objective. Okay. More precisely, objective. Oh, come on. Objective. Find estimate of x based on the measurements y that minimizes the variance. That's why it's called a minimum variance estimator. Yay! Okay. call the estimate x hat. And so we want to minimize the expected value of x minus x hat transpose x minus x hat. Okay, minimum variance. Let's do a remark. Because we know blue, do we have to make any side assumptions now? Okay. Let's just suppose we end up with a linear estimator. Just suppose that that's what we end up with. This is automatically unbiased. Got to put all the letters in the word unbiased. Because if I take the expected value of x hat, which is k times the expected value of y, equals k times expected value of cx plus epsilon, equals k c expected value of x plus k expected value of epsilon. Oh, my handwriting's falling apart, even worse than normal. I'm too excited to get to the real result, but x has 0 mean, epsilon has 0 mean, so this is 0, and so the mean of x hat is equal to the mean of x. Okay, this is 0. And that's the expected value of x. Okay, so we don't have to have any side conditions now, like kc equals identity. We don't need that. Okay, so there's no side conditions that we have to put on. Okay? Okay, so now I'm going to build an inner product space for you where the inner product gives us the variance of random variables. And so I just need to remind you guys of some stuff. So you were very happy and did quite well with things like span of 1, t squared, t to the 11 or whatever, okay? You no longer say, hey, this is a scalar, how can they be linearly independent, right? You're quite happy with those are functions, and functions, even if they take values in the reals, they can be linearly independent vectors. You guys are totally cool with that, okay? So, this is the thing about random variables that many of us forget. Random variables are functions. Okay, so if I have x, and I'm going to write it as little x's, and this is the only problem where we tend to do that. Each of these random variables is mapping a probability space into the real numbers. So the probability space, I mean, when I roll a dice, it's all of the subsets of the numbers 1, 2, 3, 4, 5, 6. It's a set of my outcomes, and I have probabilities on that. For us, when we're doing normal random variables, omega is the reals, okay? So for normal equals Gaussian, just so you don't think normal means usual, okay? Random variables. Omega equals reals. And omega has a name. It's called the probability space. My probabilities measure the size of subsets of omega. So I just want you to think about the components of X as functions, and then when I write down the following vector space, you won't be freaked out. So here's my field, just the real numbers. I'm going to create a set of vectors, whoops, because I want to take the span. All the linear combinations I can generate from x1, x2, xn. Okay, so this is a function just like 1. This is a function just like t. This is a function like t to the n minus 1. Okay, so those are functions. I can treat them as vectors. So I have random information about the x's, and I have random information about the components of the noise. So epsilon equals epsilon 1, epsilon m, and as I said before, x. So that is a vector space. That is a vector space. I'm going to turn it into an inner product space by defining an inner product. Okay. I'm going to define the inner product so that the norm squared of a vector in X is equal to its variance. Okay? So this is the key to everything, is having the abstract setup where we're comfortable with working in inner product spaces. We first define the vectors, we define something, and then check that it's really an inner product, and then we can do minimum distance best approximation problems. So if I can put an inner product so that the induced norm is equal to the variance, okay, the square of the norm is the variance, then when I do minimum variance problems, I just do best approximation problems in this inner product space, and I get everything from the normal equations. Everything follows from the normal equations. Okay? So if Z1 and Z2 are vectors in X, I'm going to define the inner product of Z1 and Z2 to be the expected value of Z1 times Z2. Okay? Let's note if Z is in X, that implies expected value of Z is equal to 0. That's because we have z equals, let me call it gamma 1 x1, gamma n xn, gamma n plus 1 times epsilon 1 plus gamma n plus m times epsilon m. That's so ugly. N plus m. Okay. So things in X are in the span, so they're linear combinations of the components of my unknown X and the noise term. Okay? And so the expected value of Z is just the expected value of the sum, and each one of these has 0 mean, so the mean of Z is 0, okay? So it's the expected value of a sum of things is the sum of the expected values. The integral of a sum is the sum of the integrals, okay? And then the variance of Z is, well, excuse me, I want to define the norm squared of Z. So that's the inner product of Z with itself. So that's the expected value of Z squared. And that's the variance of Z because Z has 0 mean. Okay, so my inner product is the correlation between two random variables. It's the expected value of Z1 and Z2. Did you see that one coming? Okay, so this is why I call it the unexpected inner product. It's an expectation, okay? It's just a play on words. A little bit of mathematical humor. You can use it in a cocktail party.
Totally expected this.
Totally, okay? Okay, so to calculate the inner product of two random variables, we looked at their correlation, okay? So our vector space consists of all of the random variables that we have in the problem. Let's go back and look at the problem. The stochastic assumptions are on X and epsilon. The 0 mean means when I put all the components of X and epsilon, they all have 0 mean. Okay, so their variances are just expected value of xi squared and expected value of epsilon I squared. We know the expected value of epsilon I times xj, that is 0. They are uncorrelated. Okay. And my measurements, each component of y is just a linear combination of the x's and the epsilons. Okay? Each component of y, when I write that out, each component of y looks like a row of C multiplying the x's plus one of the epsilon i's. That's what the ith component of y. So y is just linear combinations of my random variables. So with y, I can generate a subspace. So, okay. So if I minimize the norm in here, I do minimum variance. That's what I'm after. I define M to be the span of the components of y. So that's a subspace of X. This is a subspace. And so my best estimate X hat, its ith component is just arg min M and M, some linear combination of the measurements, norm xi minus m, and we can put a square there if we want. Okay, so this is now a minimum variance estimate of X. So this is the minimum variance estimate of the ith component of X as a function of a linear combination of the measurements. So that's what we're after. And we know how to do that. We just write down the normal equations. Okay. So to solve this, we just write down the normal equations. Okay, so this is totally cool. To deal with the stochastic problem, we're now going to do an orthogonal projection in an inner product space, and we're totally fine with doing those things, okay? So let's just see how that works out. Okay, so I'm going to have x hat I equals alpha 1 hat times y1 plus alpha 2 hat times y2 plus alpha m hat times ym. Okay. So that equals alpha hat transpose times the vector y, where alpha hat, I just stack up my components. Okay, so xi is a row vector times the column vector y to get a scalar. And so the row vector is the transpose of this. Okay, and then I have that the alphas satisfy g alpha hat equals beta. If I put I can put the transpose here if you like it. We can take it out if we don't like it, because G is symmetric. And the ij element of G is equal to the expected value of yi times yj. Right? We take the inner product of the basis vectors for the subspace M. M is the span of y1 to ym. So that's the inner product, okay? So that's the inner product of yi with yj. So let's just calculate what this correlation coefficient is. Okay, so we have y is y1 to ym. That's cx plus epsilon. So it's the first row of C, second row of C, mth row of C times x plus epsilon 1, epsilon 2, epsilon m, right? So all I did was decompose C into its rows. Okay, so let me let you catch up. So yi is just the ith row of C times the x's plus epsilon I, and then yj is the jth row of that. So let's just now calculate the ij element of G, which is inner product yi yj equals expected value yi yj Now all I'm going to do is substitute in for what those scalars are. And I have Cix plus epsilon I, Cjx plus epsilon j. Okay, no typos yet. I make a lot of them usually. So we're just breaking down each of these scalars into the components of y, writing them down in terms of the rows of C in the individual entries in X and epsilon. And so what do we get here? Let me see, I'll break it all up. Yeah, so let's do that. So let's just multiply it out. We get Cix, Cjx, plus Cix epsilon j, epsilon I Cjx plus epsilon I epsilon j. Okay, we have an assumption that the x's and the noise terms here are uncorrelated. So these are zero. These expectations of mixing the x's with the epsilon, these two terms are zero. This is the ij element of the covariance of the noise. That's qij. What's this one look like? Huh, okay. So we get 0 and 0 when we do those expectations. Well, Cix, if I write this one as Cjx transpose, I don't say change anything, because Cjx is a scalar, okay? And the reason I want to do that is Cix x transpose Cj transpose plus epsilon I epsilon j. Now I get something really interesting. So Ci comes out, expectation of x transpose, Cj transpose comes out, and then I have Qij for that term. Okay, so Qij is inner product, is expectation epsilon I epsilon j, and this is P. So this equals Ci P Cj transpose plus Qij. And so what does this equal? This is Cp C transpose plus Q Ij entry. Okay? Take the ith row of C times the jth column of P times C transpose. That gives us the Ij element here, and then that gives us Qij. Okay? So here's the Gram matrix. G equals C, P, C transpose plus Q. Aha, that's cool. Now, write that, and let's go back and look at our stochastic assumptions and see where that funny assumption that we had comes from. Objective, okay, okay. So this is the Gram matrix. It's positive definite, so what do we know about its determinant? It's not zero. When you build a Gram matrix by a set of vectors, what do we know is equivalent between the set of vectors and the Gram matrix being non-zero? Come on, say it. Linear independence, right? Okay? So we've always written y as span of y1 to yk, and we were thinking of those as like column vectors, functions, whatever, okay? Now they're random variables, which are functions as well. And so this, by assumption, is positive definite, and what that means is that the measurement components are linearly independent, okay? So that's cool. Okay, so that's if and only if. So really the assumption was set up so that the noise model on the state and the measurements resulted in linearly independent measurements. Well, that's cool. Okay, so for the normal equations, we need G alpha equals beta. So what does beta equal to, okay? So the jth component of beta is the inner product of xi, the thing we're trying to estimate, with the jth component of our basis for y. So that's expected value of xi, and then we put cj x plus epsilon j here equals expected value of xi cj times x, expected value of xi epsilon j, that's 0. This is a scalar, so I can transpose it. I don't change anything. Okay, and so this is the ith column of P times Cj transpose. Okay, so you can check that, but that's the ith component of x times x1 will get you all that to work out. Okay, Grizzle, admit your mistake, okay? I did not want to transpose that. Sorry. It's on tape, you might as well just admit it. You can't hide, I cannot want to write it this way. This is correct, but it's not the way I wanted to write it. Boo-hoo, okay? Yeah. It's xi. Yeah, so I want to write this like this, the beta I. Once again, inner product xi, beta j with yj. I'm going to redo it. Expected value of xi cjx plus epsilon j equals expected value xi cjx plus xi epsilon j And what I was supposed to notice, this is a vector, this is a row vector, this is a scalar, so the scalar can go inside. It's a scalar, okay? So this is Cj expected value xi(x) plus expected value of xi epsilon j. That one is 0. And so this is Cj times pi. Now, what I wrote down before is not incorrect because this is a scalar, so its transpose is what I had written down. Okay, and P is symmetric, so the ith row and the ith column are the same. Okay, it's symmetric, but this is the better way to write it. Okay, so we have G alpha equals beta. Alpha hat is G inverse times beta. And so we get alpha hat equals C plus C P C transpose plus Q inverse times C times PI. Okay, and then a few more steps. Gives, well, post all of them, we end up with x hat equals k times y, and k is equal to p c transpose times c p c plus q inverse, okay? So there's a few more steps of doing transposes and everything, but we see exactly how we have to transpose the alpha, remember, to multiply it times y. And so then we stack all those things up in rows and we get x, each of the components of x. Okay, so that's the final form of the answer. No, that's not what I wanted to do. I want to stay with you. I want to insert. Please, let me do it. Yay. Images. Today. Facts. Okay, so I'll post all these derivation where these exercises and stuff are coming from. So now we compute the covariance matrix of our estimate. And what I want to point out is it's the covariance matrix that we had to start with. So if we don't take any measurements, that's the uncertainty in X. And then that uncertainty is reduced by this term. So this term really represents the value of the measurements in reducing the uncertainty in X, okay? So that's the, oh, come on. Come on, no. Okay. So that's the a priori uncertainty in the unknown X. This is the uncertainty in the measurement after taking, in the estimate after using the measurements, okay? So this is the posteriori uncertainty, meaning after. Uncertainty. Life is hard. Okay. So we've reduced the uncertainty by using the measurements, and so this literally quantifies the value of the measurements. If you assume Q is positive definite and P is positive definite, then you certainly get that CPC transpose plus Q is positive definite. Then you can apply the matrix inversion lemma, like you anticipated, okay? And then you can compare everything between blue and the minimum variance estimator, okay? So this is what blue looks like. And then this has a different form here. And so you can see that in blue, the information matrix on the state is 0. Okay, the information that you have a priori about X is 0. That's the information matrix of X. And so what does that mean? If the inverse is 0, you can think of P as being like infinity times the identity, because 1 over infinity is 0. Okay? When you do blue, best linear unbiased information, what you're telling yourself is you have no a priori idea about how X is distributed. It can be anywhere. Its mean is 0, but it's equally likely to be close as to be far away. Okay? So when you give yourself side information about X, you actually that's how you get you're reducing the overall uncertainty in your estimate. So it's pretty cool. So blue, which we thought was already interesting because it showed us how we get the information matrix in here when we do weighted least squares, is still kind of strange because we're not giving ourselves any a priori idea about the spread in X. We're assuming it's equally likely to be anywhere, equally likely to be anywhere. And so with minimum variance, we're actually giving ourselves a positive definite matrix here that's finite, it's not infinite. And so its inverse, the information matrix, is still further reducing the uncertainty in the measurement. So that's cool. A question? Yeah.
Previously, when you were calculating alpha hat, alpha hat, your final equation of it, should that just be P for alpha hat?
So let's skip my notation. So we were looking at each individual component of X. The solution of the normal equations gives us something that multiplies the y's. So this is what you're talking about, the alpha I. So it's really indexed by here, but if I put another subscript on here, it's going to drive you guys crazy. So that's what I'm getting at there. And so you really need to solve this problem for each component of X, but the Gram matrix is the same for all of those problems. And then it's the beta that changes when I change components of X, I change this, and so instead of having P1, the next time I'll get P2, then I get P3, and so when I stack them all back up, I recover my full X covariance matrix. Is that what you're getting at? Yeah, I skipped those steps because, I don't know, I got bored. But I confused you. Sorry about that.
So this here is just for xi.
So this is the final one because this is a matrix K that multiplies Y and recovers X. Okay. So I said a few more steps, so I'll post all those. We can go through them.
This is different from the K that's given in the thing we just posted onto there. So if you scroll down. That K is that.
When you apply the matrix inversion lemma, that's what you get, okay? Yeah. That's what you get. So here's the K here, and then when you apply the matrix inversion lemma to CPC plus Q, when Q is invertible, oh, there's a transpose missing here, CPC transpose. Okay. That's what you get. And then when you apply the matrix inversion lemma, the two answers between blue and MVE look exactly the same, except for this term here, which is the information matrix, okay? And so the more information you have, the bigger this is, the smaller the inverse is, so you're reducing the covariance in your estimate. So MVE will produce an estimate with smaller variance than blue, but you need the side information about how X is distributed. If you have no side information, then X is equally likely to be far away as close. And so you're saying the information matrix is 0, so the covariance matrix is unbounded. That's the interpretation I was wanting to get to. And I skipped the steps in between, which was kind of bad. Because for me, what's really studly about this problem is the really cool vector space that we build of random variables, defining an inner product that's equivalent to minimum variance, and then just writing down the normal equations. And so we worked out almost all the components. Now you just got to put those few little pieces together to get that final answer. Okay, so that's what's going on there. And then the interpretation of how, we know how weighted least squares relates to blue. Now I'm showing you how best linear unbiased estimate relates to minimum variance, and it comes from the side information in the model. So. Okay, cool. Let's do one more little thing, and then we'll do something fun. For me, this has been fun. Let's do a random variable, X and Y. Okay? So because X has 0 mean and so does Y, the expected value of Z is the 0 vector. Okay? So let's compute the covariance matrix of Z. So that's the expected value of Z times Z transpose. So that's the expected value of X, Y times X transpose, Y transpose. Okay, so this is a matrix, it's a block 4 by 4. We have X times X transpose, X times Y transpose, Y times X transpose, and Y times Y transpose. Okay. X, expected value of this matrix. X, Y transpose, Y, X transpose, Y, Y transpose. Equals. That's a small little exercise. Let me just write down the answer to it. Okay, so expected value of X times X transpose, that's the covariance of X. It won't take you long to get that. That's P times C transpose. This is the transpose of that, and P is symmetric, so it's C times P. And expected value of Y, Y transpose, that's that Gram matrix we just computed. Okay. Let's compute the Schur complement of P in this matrix. We didn't give it a name. Okay. You guys remember the formulas by heart almost? So it's going to be P minus PC transpose CPC PPC transpose plus Q inverse times CP, right? That's the Schur complement. So we get P minus PC transpose
The whole thing inverted?
Oh, yeah, sorry. Okay. That's the Schur complement of P in that covariance matrix. Okay? It's this. Okay? The Schur complement of P, you see, X has a variance. Y is related to X. It's correlated with X. Here's the correlation between X and Y transpose, okay? So the variance in X, when we project it down onto the span of Y, is the Schur complement of P. And so this matrix here has smaller eigenvalues than the original one, okay? It reduces the uncertainty in X. Okay, so this is the covariance of X projected onto the span of Y. It's a Schur complement. So this is a nice, positive, definite matrix, okay? So I thought that was kind of cool. Schur complement, okay? Reducing the uncertainty in X through the measurement Y, you see a Schur complement. We will get this later as the conditional variance of X given the measurements Y. So we have to do conditional random variables, but it all comes back to Schur complements. That's part of the reason we do them. Okay, okay, so we're done with MVE. Okay. If there's questions, we can do that. Otherwise, I want to tell you that you've been using a horrible version of Gram-Schmidt, okay? I'm going to break your hearts that I had you on the exam using a numerically unstable algorithm. Oh, why'd you do that to us? Well, this is because everybody teaches you that algorithm, and only I tell you that there's a better one. I just want to point it out. So everything that we're on here will never be on the final exam. It's stated on the handout when I posted. This is not on the final exam. I did not want to cover this before your exam on Tuesday because I didn't want you using the modified Gram-Schmidt because it's harder to do the calculations. I didn't want to sow confusion in the class, okay? So this is just for awareness. So I'm going to take three vectors that are nearly linearly dependent when epsilon is small, right? When epsilon goes to 0, it's 1, 0, 0, 0. They're linearly independent for every epsilon positive or non-zero, in fact, okay? So what I'm just going to do is rewrite these using the standard unit bases, okay, for R4. So Y2 is really Y1 plus this, and Y3 is Y2 plus this. You can just go and plug them in and check it. And so the span of y1 and y2, okay, is the same thing as the span of y1 and this new information that was added. As long as epsilon is non-zero, I get this. And the span of y1, y2, y3 is y1 and these nicely linearly independent vectors. Okay, so they generate the same span, is what I'm showing. So if I apply Gram-Schmidt to these vectors and I apply Gram-Schmidt to these vectors, what should I get? I should get the same thing. They're the same vectors, okay? So I just do it, okay? I go to MATLAB and I take epsilon equals 0.1, and sure enough, I get exactly the same thing comes out for Gram-Schmidt applied to this set of vectors and this other set. They have the same span. And then I said epsilon equals 10 to the minus 8, and the difference in the orthonormal vectors I get out of Gram-Schmidt is big now, okay? Okay, so here's the classical Gram-Schmidt algorithm with normalization. So you guys didn't do the normalizations on Tuesday. So I just set V1 equal to Y1 and I divide by its norm 1. Then I subtract off the projection of Y2 on V1. I don't need to divide by the norm of V1 because it's already 1 and multiply it times V1. So this V2 is Y2 minus the projection of Y2 on V1. Then I make that length 1. And my new vector V3 is Y3 minus the projection of Y3 on V1 minus the projection of Y3 on V2. And then I normalize that. So that's the standard Gram-Schmidt. Okay? And so there's the algorithm on the other side, but this is just writing it out so you guys see exactly, yeah, that's our Gram-Schmidt. We normally don't do this, so we have to divide by inner product V1, inner product V2 with itself, inner product V1 with itself. So that's fine. It's the Gram-Schmidt we know and love. And then we just run it. And like I said, here's Gram-Schmidt applied to Y1, Y2, Y3. And this is the QR factorization of taking Y1, Y2, Y3 as a matrix. And notice that the R is telling us that these things are almost linearly dependent because to 4 significant digits, R is 1, 1, 1. It has rank 1. Whereas the other vectors are nicely linearly independent. R is clearly nicely invertible. So, but we should get the same orthogonal vectors, and we don't. So here's what's called the modified Gram-Schmidt. And all I want you to know is that this algorithm exists. Okay? And when you go to some other class, use this. This is the one you program up when you need to do Gram-Schmidt. Okay? Because it's numerically well behaved. So it's just a little bit different, but you can see it's kind of the same thing. V1 is Y1 divided by the norm of Y1. So the first thing we do is we just rename the Y's as V's, okay? That's all we're doing here, the first step. We just rename the variables. But then what it does is it removes the V1 component from all of the other Y's. So for V2, V3, V4, etc., we remove the V1 component. That makes V1 orthogonal to V2 through Vn by doing that. We've removed the V1 component. Okay? And then we get V2 by normalizing it. And then we remove the V2 component from all of the other vectors, and we have V2 orthogonal to now V3, V4, Vn. And then we normalize that. So that's what this algorithm is doing. And when you do that, even when you're using 10 to the minus 8 and stuff like that, you get that the the algorithm produces exactly the right thing. Okay, so here's the orthogonal vectors for these very terribly conditioned components. And here's the orthogonal vectors for the nicely conditioned representation of the span. And what's different, okay, so it produces the right orthonormal vectors, and you can still see the original ones were nearly linearly independent because when you do the QR factorization, the rank of this matrix is very poorly, but you get the same orthogonal vectors. Okay, so it's more numerically stable. So I just want you to know there's a poor way to do Gram-Schmidt, but it's easy theoretically to understand the calculations. And on your final exam, that's the one you use because it's super easy, okay? You will have forgotten this one by the final, so I'm not going to cause any confusion on the final exam. So I'm very comfortable with that. But if someone ever asks you to do the calculations, please remember to use modified Gram-Schmidt. MATLAB does it automatically if you use its toolbox, okay? That's what it's doing, that's all. So this is all you need to know for the final exam, right here. So, true-false question, all Gram-Schmidt algorithms are equal. False, okay? So it's not like regular induction and strong induction. Those are equivalent. These two algorithms, they're not numerically equivalent. Theoretically, yes, but numerically they behave very differently. So that's it. Okay, thank you. I used up, I got 8 minutes left. Happy to answer questions if anybody has questions, and that's it for today.